Welcome to my lecture on polar curves. Suppose we are given a point P in the plane. The location of this point P can be determined by using a pair of coordinate axes, the x and y axis. This is called the rectangular coordinate system. The location of P is indicated by the coordinates x, y, where x refers to the abscissa and y as the ordinate. The abscissa is simply the distance of the point P from the y-axis, while the ordinate y is the distance of P from the x-axis. Supposing that we have point P sub 1 with coordinates 3, 4. So that means that the location of P1 is 3 units from the y-axis and 4 units from the x-axis. That determines the location of P sub 1. If we take on another point, say P2 with coordinates 2, -1, the location is 2 units from y and 1 unit below x. That is the location of P sub 2. We can make an extension of the location of a point in three-dimensional space, wherein we have the coordinates axis x, y, and z. For this point P, the x-coordinate will be 1, 2, and 3. The y-coordinate will be 1, 2. And as for the z-coordinate, it will be 1, 2, 3, 4, 5, and 6. So that gives us the exact location of point P in three-dimensional space. Let us now discuss another coordinate system that will determine the location of a point in a plane. So supposing that we have a point P with coordinates x, y. Let the origin be called as our pole, and the horizontal axis, let us call this as OX, as our polar axis. The distance of the point P from the pole is to be denoted by R, which is sometimes referred to as the radius. Let theta be the angle that line OP makes with the polar axis. Now the point P can be represented by the pair R, theta. R, theta are the polar coordinates of point P. And from this, we can establish the relation between the rectangular coordinates x, y, as well as the radius r and the angle theta. This is equal to y and this is equal to x. If we are to take on sine theta, that is equal to y over r, where y is equal to r sine theta. Taking now cosine of theta, that will be equal to x over r, where x is equal to r cosine theta. Another relation is that by applying Pythagorean theorem, we have x squared plus y squared is equal to r squared. So again, a point P can be represented by a pair of coordinates r, theta called the polar coordinates, where r is the radius and theta is the angle that the line makes with the polar axis. Unlike in the polar rectangular system where every point in the plane has only one pair of coordinates, there are several ways or several polar coordinates that may represent a point. So let us consider a point P with polar coordinates r and theta. So r is the radius and theta is the positive counterclockwise angle measured from the polar axis. You can call this as OX. Now let us give a specific value to r and theta. Let us say 5 and 50 degrees. So the radius is 5 units and the positive counterclockwise angle is 50 degrees. Okay. Now, if we are to add 360 to 50 degrees, starting from the polar axis, we will be getting the same terminal side. So coterminal to 50 degrees is 50 degrees plus 360 degrees equivalent to 410 degrees. So the polar coordinates 5, 50 can be represented by the polar coordinates 5, 410 degrees. So this is another pair of coordinates corresponding to the same point P. So if we are to add any multiples of 360 to the angle theta, we will be arriving at the same point P. So we can generalize this and write this as 5 plus or 5 angle 50 degrees plus 360 degrees times k, where k is any positive or negative integer. Positive or negative integer. Alright, so it will give you the same point P. Another is this. If we are to measure this angle from the polar axis in the counterclockwise direction, that will be equal to negative 310 degrees. So another pair of coordinates for that same point P will be 5, negative 310 degrees. Alright? Still another is, if we are to consider this positive angle, that will be equivalent to 180 degrees plus 50 degrees or 230 degrees. So that is a point exactly opposite to point P. If we are going to negate the radius of 5 units, we will be getting the same point P. So we have another way of expressing the coordinates of that same point P, and that is negative 5 and 230 degrees. Still another is this angle. That angle is equal to negative 130 degrees. This being equal to 50 degrees. So the point is again exactly opposite to point P. So another way of expressing the coordinates of P will be P -5, and -130 degrees. So this only shows indeed that any point in the plane can be represented by several pairs of polar coordinates. So remember that if the angle is measured in the counterclockwise angle, it is positive, and if it is measured in a clockwise angle, it is negative. If R is positive, then the point is at the terminal side. But if R is negative, it is located opposite of the terminal side. So this is a polar coordinate paper comprising of radial lines emanating from the pole, and the indicated angles are the counterclockwise angles measured from the polar axis. Of course, we also have these concentric circles of different radii. These are for the radii or the distances of the points. So, say we are to plot the following points. We can start with, say, P1. The coordinates are 8, 120 degrees. So, we can start with the radius distance of 8 units on the polar axis. That will be 2, 4, 6, and 8. And then we turn around in a counterclockwise direction 120 degrees. So this is supposed to be the point. So that is the location of point P1. Next, say for example, our P sub 2 has coordinates of 4 and -45 degrees. So we can start with the angle -45 degrees. Since it is negative, it should be in the clockwise direction. So 15, -15, -30, and -45, and then 4 units. So we count 4 units. We count 4 units. 2, 2, and 4. Okay, let me change the color. Let me use a red one. So that is the location of P sub 2. We go to the next one, P sub 3, say -6 and 210 degrees. So -6, 210. We can start with the angle, +210. So there is +210. But since our R is negative, it must be at the opposite side. Okay? So it should be 210, +210. The opposite side is equivalent to 30 degrees. So we count 6 units. So 30 degrees and then 2 units. Or rather 6 units. 2, 4, and 6. That is our P sub 3. Finally, let us say that P sub 4 has coordinates of -10 and -90 degrees. So -90 in the clockwise direction, that is equivalent to 270, and since it is -10, it should be at the opposite side. So 2, 4, 6, 8, and 10. So that must be the location of P sub 4. This is another example of a polar coordinate system where the angles are expressed in radian measure. So for the given points P, Q, and R, let us indicate their coordinates. So for P, we have 1, 2, 3, and 4. and the angle is pi over 3. So 4 pi over 3. Pi over 3 is equivalent to 60 degrees. Just take note that pi is equal to 180 degrees. Okay, let us now go to point Q. Point Q, 1, 2, 3, 4, and 5. 5 units, and the angle is 5 pi all over 6. So Q, 5 and 5 pi all over 6, which is equal to 150 degrees. Okay, and then R, point R is 1, 2, 3, 4 units from the pole, and the angle is 4 pi all over 3. So R is 4 and 4 pi all over 3. Now, at this point, let us express the coordinates of P, wherein R is negative as well as theta. So both R and theta are negative. Okay, so that will be for the angle, it is pi over 3. The angle must be opposite, so it should be equivalent to 4 pi over 3. Now this is of course 30 degrees or pi over 6, and this one is pi over 2. So that will be equal to 120 degrees or 2 pi over 3. Okay, so P is negative 2 pi over 3, and then opposite negative 4. Okay, so this is another way of expressing the coordinates of P, where R and theta are both negative. You can try this on the other points Q and R. Let us now draw the graph of R equal to 4 plus 4 cosine theta. Now, what we will employ here is point plotting. We will be substituting values to theta, and we will calculate for the corresponding R value. And then we will plot the polar coordinates. So we can start at theta equal to 0. So your R is equal to 4 plus 4 cosine of 0. We know that cosine of 0 is 1, so that will be equal to 8. So we have the point 8, 0. Then theta equal to 30 degrees. R is equal to 4 plus 4 cosine of 30 degrees. Cosine of 30 degrees is 0.866 times 4 plus 4, roughly that will give us 7.5. So we have 7.5, 30 degrees. So for theta equal to 45 degrees, R is equal to 4 plus 4 cosine of 45 degrees. Cosine of 45 is 0.707 times 4 plus 4. That will be about 6.8. Then next, theta 60 degrees. So R is 4 plus 4 cosine of 60 degrees. Cosine of 60 is 1/2 times 4 is 2, and 4. That will give us 6. So we have the point 6, 60 degrees. Now the other one is 6.8, 45 degrees. So we continue at theta equal to 90 degrees. So R is equal to 4 plus 4 cosine of 90, but cosine of 90 is 0 times 4 plus 4, that will give us 4. So we have the point 4 comma 90 degrees. So we continue to do that by substituting values to theta. We can try 120 degrees, 150, etc., up to 360 degrees. And for this, we can create a table. So these are the table of values for theta and r. Then we are going to plot each of these. No? For theta equal to 0, your r is 8. For theta 30 degrees, 7.5, and so on and so forth. And this will be the graph. This is called a cardioid. No? So at theta equal to 0, that will be 8 units. No? 2, 4, 6, and 8 units. For angles 90 down to 180, notice that r diminishes in value and that becomes 0 at 180. And you can also notice that there is symmetry with respect to the polar axis as exhibited in the values in our table. No? So at 150.5, at 210.5, at 135, 1.2, at 225, 1.2, and so on and so forth. No? So you can abbreviate the computations if you know the symmetry of the curve. The equation of a cardioid may take any of the following form. R is equal to A times 1 plus or minus cosine theta, or R equal to A 1 plus minus sine of theta. So this one, for this one, the equation is R equal to A times 1 plus cosine of theta. The next one, R is equal to A times the quantity 1 minus cosine of theta. Then R is equal to A 1 plus sine of theta. And finally, R equal to A times 1 minus sine of theta. Now in some books, they use the expression R equal to A plus minus B sine theta, or R equal to A plus minus B cosine of theta. In this case, your A over B, or the ratio A over B, must be equal to 1. Let us now discuss about a LIMACON. The equation of a LIMACON is R equal to A plus minus B sine theta, or R equal to A plus minus B cosine theta, where A over B, or the absolute value, is between 1 and 2. Now, this is a LIMACON with a dent. No? It's a LIMACON with a dent. We know that if A over B is equal to 1, that is a cardioid. No? So for the case wherein the ratio A over B is between 1 and 2, then it will be a LIMACON with a dent. Now for this particular LIMACON, the equation of which is R equal to 3 plus 2 sine of theta. Notice that when theta is 90 degrees, sine of 90 is 1 times 2 is 2 plus 3 is 5. No? It is maximum when theta is 90 degrees. Now, how about for 270 degrees or negative 90 degrees. Sine of negative 90 degrees is negative 1, times 2 is negative 2, plus 3 is positive 1. At 0 and 180, the value of sine theta is 0. So your R is equal to 3. Next is a convex LIMACON. You have a convex LIMACON if the ratio A over B, or the absolute value, is greater than or equal to 2. So the equation is still R equal to A plus minus B sine theta, or R equal to A plus minus B cosine of theta. This is a convex LIMACON. And the equation of the convex LIMACON here is R equal to 2 plus sine of theta. Maximum, R is maximum when theta is 90. So maximum value of sine theta is 1, and 2, that would be 3. And when theta is negative 90, sine of negative 90 is negative 1, plus 2 is positive 1. We now go to the last case for LIMACON, that is when the ratio A over B is between 0 and 1. It results to a LIMACON of 2 loops. So the equation is R equal to A plus minus B sine theta, and R equal to A plus minus B cosine theta, where the ratio A over B is between 0 and 1. So this is the graph of R equal to 1 plus 2 cosine of theta. The big loop is generated, the upper portion of the big loop up to this point is generated from 0 to 120 degrees. The lower part is generated from 0 to negative 120 degrees. Now, the smaller loop is generated between 120 and 240 degrees. Okay? So, supposing that your theta is 180 degrees, cosine of 180 is negative 1, times 2 is negative 2, plus 1 is negative 1. So the angle is 180, but since R is negative, it is at the opposite side, and that will be the point. Alright? So again, the big loop is generated from negative 120 degrees to positive 120 degrees, while the smaller loop here is generated from 120 degrees to 240 degrees, where R is negative. So for this one, the equation of the LIMACON is R equal to 1 plus 2 sine of theta. Next is the spiral of Archimedes, and this is the graph of the spiral of Archimedes, and the equation is simply R equal to theta, where theta is in radians. So for theta equal to 0, R is 0, that is the pole. Then 30 degrees, that is equivalent to pi all over 6. So that is 3.14 over 6. And then for theta equal to 45 degrees, that is pi over 4, or 3.14 over 4. For theta equal to 90 degrees, that is pi over 2 or 3.14 over 2. So as theta increases, so is the value of r, and at 360, that is equal to 2 pi or 6.28. Of course, you can continue for theta higher than 360. So it is an ending spiral, for various values of theta. Next, the graph of r equal to a sine 2 theta and r equal to a cosine 2 theta. So here is the graph of r equal to a sine 2 theta. Notice that when theta is 45 degrees, 2 times 45 is 90, and sine of 90 is 1 times a, or r equal to a. So maximum r, or the value of r is maximum when theta is 45 degrees. And of symmetry, notice that we'll be getting the same maximum value for r equal to a when the angles are 135, 225, and 315 degrees. Next, for r equal to a cosine 2 theta, we have an identical graph, no? But maximum occurs at theta equal to 0, 90, 180, and 270. So again, there is symmetry with respect to 0 degrees, 90 degrees, or 270 degrees. Now we refer to this as 4-leaved roses or 4-leaf roses. Next are the 3-leaved roses. R equal to a cosine of 3 theta and r equal to a sine 3 theta. So it's obvious why it's called a 3-leaf rose. No, there are 3 leaves or petals to our rose. Notice also the coefficient of theta equal to 3. For the following polar curves, r equal to a sine 4 theta and r equal to a sine 7 theta, notice that for r equal to a sine 4 theta, there are 8 leaves in the graph, equivalent to twice the coefficient of theta. On the other hand, for r equal to a sine 7 theta, notice that there are 7 leaves in the graph. So we can make a generalization that for r equal to a sine k theta, or r equal to a cosine k theta, if k is even, then there will be 2k leaves. But if k is odd, there will be k leaves. Alright, so if you have r equal to a cosine of 5 theta, this will indicate that there are 5 leaves in the graph of the polar curve. For r equal to a sine of 6 theta, this will indicate that there will be 12 leaves in the graph of the polar curve. Let us take on a special case for r equal to sine k theta. If k is equal to 1, then what will be our polar curve? R is equal to a sine theta will be a circle. So when theta is 0, sine of 0 is 0 times a 0, so r is 0. That will be the pole. For increasing angles up to 90 degrees, the value of sine theta increases and maximum is 1, no, at 90 degrees, so that will be equal to A. For angles from 90 to 180, the value of A will decrease and it will become 0 at 180. For angles from 180 to 360, you will be getting a value of sine theta that is negative. So R is negative and it will be a point opposite to the terminal side, generating again the same points generated from 0 to 180. Now for R equal to A cosine theta, it will also be a circle, maximum when theta is 0. So for both cases, the radius of the circle will be equal to A all over 2. If R is equal to negative of A sine theta, then the circle will be located down below the polar axis. And for R equal to negative A cosine theta, it will be a circle tangent to the line theta equal to 90 degrees at the opposite side. Okay. Next are the lemniscates. So we have here 4 different lemniscates. The first one is R squared equal to A squared cosine 2 theta. Observe that the graph appears only from negative 45 degrees up to positive 45 and 135 up to 225. Since it involves R squared, then the right side must be positive. So cosine 2 theta is positive only for negative 45 to 45, 135 to 25. For 45 up to 135 and 225 up to 315, cosine of theta is negative. That explains why there is no graph on these ranges of angles. For the second one, R squared is equal to negative A squared cosine 2 theta. Since again, the right side should be positive, since it is preceded by a negative sign, cosine 2 theta must also be negative. And that happens when theta is from 45 up to 135 and from 225 to 315. We can make the same arguments for the other two lemniscates. So here is the graph of R equal to secant theta, which is a vertical line, and R equal to tangent theta. Next are the graphs of R equal to cotangent theta and R equal to cosecant theta. Let us consider this curve whose equation is R equal to 2 all over 1 plus cosine theta. Let us determine the corresponding equation of this curve in the rectangular coordinate system, meaning the equation in terms of x and y. We know that x is equal to r cosine of theta, as well as y equal to r sine theta, and that x squared plus y squared is equal to r squared. Alright. So r is equal to 2 all over 1 plus our cosine theta is equivalent to x all over r. So that is equivalent to 2 all over r plus x all over r, or 2r all over r plus x. So r is equal to 2r all over r plus x. We can cancel here the r. And then we cross multiply, we'll be getting r plus x equal to 2. And our r is equal to the square root of x squared plus y squared. Then let us transpose x to the left side, so that will be negative x. And squaring both sides, we'll be getting x squared plus y squared equal to 2 minus x quantity squared. Let us expand the right side. That will be 4 minus 4x plus x squared. Now we can cancel x squared. So what remains? Y squared equal to 4 minus 4x, or y squared equal to, let me factor negative 4. So that will be x minus 1. And we recognize this as the equation of a parabola with vertex at 1, 0, and since it is negative, it is opening to the left. And that is exactly what we have here, a parabola with vertex at 1, 0, opening to the left. Okay, so the equation of the parabola is y squared equal to 4 minus 4x. We have here two polar curves, a LIMACON, r equal to 2 minus cosine theta, the polar curve in blue, and the circle r equal to 2 cosine theta, the circle in red. So the idea here is how to find the points of intersection of these two polar curves. So we rewrite the equations. R equal to 2 minus cosine theta and r equal to 2 cosine theta. Both being equal to r, we can equate the 2. 2 minus cosine theta is equal to 2 cosine theta. Or 2 equal to 2 cosine theta plus cosine theta is 3 cosine theta. Equivalently, cosine theta will be equal to 2 over 3. And we can solve for theta by taking the arc cosine of 2/3, and roughly that is about 48.19 degrees. But we know that cosine of theta is equal to cosine of negative theta. So the other value of theta here is negative 48.19 degrees. Okay, so these are the two angles, positive 48 and negative 48 degrees. And we can check that by substituting these angles to theta for both polar curves or for both polar equations. R equal to 2 cosine of 48.19, which is about 1.33. Substituting the same angle of theta to r equal to 2 cosine theta, that is 2 cosine of 48.19 degrees, is also equal to 1.33. Alright, so the coordinates are 1.33 and 48.90 degrees, and the other one is 1.33 negative 48.19 degrees. Another example, we have here a LIMACON of two loops and a circle. So the LIMACON is r equal to 1 minus 3 cosine theta, and the circle is r equal to 1. So observe that there are 4 points of intersection. The first two can easily be determined by equating the two. Now, as for the other 2 points of intersection, this can be determined by considering the fact that the equation of the circle r equal to 1 can also be written as r equal to negative 1. Okay, so when theta is 0, r is negative 1, it refers to this point. So for any angle from 0 to 90, your r will be negative 1, so it will be generating all points opposite to the points in the first quadrant. Same thing for the angle 90 to 180. For each of these angles, your r is negative, so it will be generating the other quadrant of the circle. So from 180 to 360, the same thing, your r will also be negative, generating the upper half of the circle. Knowing this fact, you can equate r equal to negative 1 to r equal to 1 minus 3 sine theta and you will be able to obtain the two other points of intersection. These are supposed to be 1, comma, negative 41.81 degrees, and the other one is 1, comma, negative 138.19 degrees. Okay? Or the same point is generated if you use negative 1 and positive 41.81 degrees and negative 1, positive 138.19 degrees. For the four leaded rows r equal to 4 sine 2 theta and the circle r equal to 2, observe that there are 8 points of intersection. Okay? Because of symmetry, we only have to determine one point of intersection, and that will allow us to determine the other 7 points of intersection. So we equate the 2 equal to 4 sine 2 theta, or sine of 2 theta is 2 over 4 or 1/2. So 2 theta is arcsine of 1/2. And we know that that is equal to 30 degrees, so theta is 15 degrees. So obviously, this point of intersection has the coordinates 2 and 15 degrees. Then because of symmetry, we'll be able to identify the other 7 points of intersection. So this one will be equal to, or the coordinates will be 2 and 75 degrees. This one is 2 and 105 degrees. This one will be 2 and 165 degrees. Next is 2, 195 degrees, followed by 2, 255 degrees. Then we have here 2, comma, 285 degrees, and finally 2, 345 degrees. You may try on the following exercises. Thank you for listening.